Dear all, a very good afternoon to all. I am Dr. Srikant Chaudhary from the Sant Garjava College of Engineering and Technology, Bhusawal. It's really a great pleasure for me to introduce our today's second session speaker, Dr. Prasanna S. Gandhi. Dr. Prasanna Gandhi is a professor in mechanical engineering at IIT Bombay and also director of Suman Mashruwala Advanced Microengineering Laboratory. He received his BE degree from the University of Bombay in 1994 and the MTech degree from IIT Bombay in 1996, both in mechanical engineering. After a brief industrial research experience at Larsen and Toubro, he received the PhD degree in mechanical engineering from the Rice University, Houston in 2001. Dr. Prasanna's current research focuses on the area of polymer and ceramics, 3D microprinting, dynamics, and control of ultra-flexible mechanism systems for applications in microprinting, medical robotics, products, and devices. Among other honors, he is a recipient of third rank at Mumbai University in B 2004, Robert Lowry Patton Award at Rice in 2000, Boys Cast Fellowship in 2006 of Government of India, Professor J.R. Isaac Fellowship in 2006-2007, and Best Faculty Award in 2008. He has been a qualified teacher of stress relieving life enhancing techniques of Art of Living Foundation by Sri Ravi Shankar. He has several patents on his name. He has published more than 140 journal and conference papers. Now, I request Dr. Prasanna Gandhi sir to address us on topic innovative techniques for microfabrication. Over to you, sir.
Okay, thank you very much for this kind introduction, Dr. Shrikant. Uh, so, may I share my screen?
Yes, sir.
Okay. So, can you see this?
Yes, sir. We can see it. Only it is not in presentation mode, but we can see that.
Oh, it's not in presentation mode?
Yeah, it is not in presentation mode, sir.
Oh, can you see the slides changed?
No, sir. We are seeing all your layout, but not in presentation mode. The PPT is.
You see this thing with the black background, right?
Yes, sir. It is with a black background.
Because I have two presentations open. Maybe I'll just try again.
Okay.
Okay. Maybe it will be better I can share the entire screen. Okay. Okay, can you see now?
Yes, sir. It is in transition. Yes, sir. Now it is perfect.
It's perfect, right?
Yeah. Yes.
Okay, great. Okay. So, first of all, I would like to thank organizers for inviting me to give this talk and share some of the exciting things in the research going on at our laboratory. I really appreciate the efforts taken by the organizers to kind of organize this program and give us this kind of opportunity to share the knowledge. I know in this course you would be looking at like a lot of micro systems.
Sir, you are muted. Sir, you are muted.
Okay, sorry. Sorry, okay.
Now it's okay.
Yeah. Oh, okay, fine. So, did you hear anything, or it's just like maybe I'll start from beginning again. So I'll just wanted to thank organizers for organizing this program and giving us opportunity to kind of share some of the exciting research that is going on in our laboratories here. Um, in this program, you all would be going through a lot of these micro scale techniques and things like that. I would like to draw your attention to this different kind of a like a philosophy of thinking to. Oh, sorry, I'm getting muted. I think somehow I don't know how. Am I audible now?
Yes, sir, you are audible.
So, did you hear anything, or like no? I don't know when I got muted.
Just for a second, it is okay, sir. You can continue now.
Okay. So I'll continue. Okay. So just interrupt me if at all any problem is there here. Huh?
Yes, sir. Sure.
Yeah. So see, through this course you will be looking at different kind of techniques of microfabrication, mainly coming from VLSI based microfabrication of the chip technologies, like a silicon chip design or VLSI kind of methods of fabrication, which are adopted for the mechanical components. But here I'm going to kind of open up some different kind of purview of looking at this multi-scale kind of a fabrication, including micro and nano scales also. So we'll look at particularly this fabrication of fractal-like geometry, as you can see here. Let me get a laser pointer right here. Get this. Okay, sorry, I'm not able to get the laser pointer, but hopefully you should be able to see. Can you see my pointer? Okay. Okay, so as you can see here, these kind of fractal geometry structures which are seen in the nature widely, we are kind of looking at some of the formal techniques of controlling and fabricating these structures in a very different kind of innovative way. So my talk is focused upon that aspect, and if time permits, we'll talk about some other kind of innovative techniques also. So depending upon time, we'll proceed. So let me give you some kind of a motivation for this. And before going to that, this is a lab in which we have carried out these activities, and there is always a room for active collaborations for any of the research that would align, and I know jointly things can be done better. Okay, so this is Suman Mashwala Advanced Microengineering Lab. I must acknowledge the funding by Raj Mashwala, whose initial funding could kickstart this lab, and then of course with a lot of government funding, the lab is getting supported close to maybe about I would say about maybe 15-20 crores of the funds so far have been utilized for different activities in this laboratory. And motivation for this particular part of the research is about this nature. So see, nature has this kind of fractal geometric systems everywhere. You think of trees, you think of leaves, you think of our own kind of a circulatory system. Here you have one big vein splitting into multiple veins, and then some kind of a mass transport happens, gas exchange happens, and then again this blood comes back to the heart, and then gets purified in the lungs. So there are lot of these kind of systems nature has designed. Why nature has designed in this kind of a fashion is because they are inherently efficient. If you see, there are now recent publications also are coming for utility of these structures into actually heat transport and mass transport kind of applications, where it's shown that these are very efficient in the heat transport under very less pressure head that is required to flow the fluid through these channels actually. So nature has somehow kind of optimized these structures in our body in many other places, in animal and tree kingdoms, I mean plant kingdoms, to get these structures ubiquitously done for kind of applications or kind of utilities that they would need. In typical cases, it is like transporting the liquid or media from one place to other place and exchanging some gases or some nutrients and things like that. Say for example, in the respiratory system, very efficient gas transport happens in our lungs with these kind of very tiny kind of capillaries that are coming up in the alveoli of the lungs. So these structures have a lot of these advantages. Very high surface area to volume ratio is one of the main characteristics of these structures. And at the same time, typically when you do this high surface area and volume ratio is high, then for the flow to happen to such a kind of a geometry, you will need a lot of pressure head. But in these particular cases, it is known that this under very low pressure head, these structures can work. And that's why the optimality is there for the nature to drive the fluid and get the phenomena of mass transport happen very efficiently in terms of the kind of amount of power that is required. And so these are some of the applications of these structures. So organ on a chip or synthetic leaf you can produce, or cell sorting, plasma separation, that kind of application, chip cooling application for the semiconductor industry, and things like that. Several applications can be possible. Now, in the third dimension, if you stretch, you can have these structures to have these structural supports done in a very elegant kind of a manner. So normally the beams that you need to design for the buckling, now they can be, since we have a 3D printing market coming up very fast, you can have these kind of geometries very easily possible now in construction industry also, or in our day-to-day life products also. And this geometry will have very less material, which will kind of get uniformly stressed everywhere with an equal stress, and it will support the structures in a much kind of efficient way, saving the material that is required to do this job. Okay, so and also it gives some kind of elegance or some kind of aesthetic sense to the designs that has been done in this is architect in the UK who has kind of proposed this and developed these structures. So now let's come to the fact how do we manufacture such kind of a thing. So aspects of the structure that are to be seen here is they have fractal-like nature. They have microscale geometry typically towards the end, and then they have multi-scale kind of a nature. Okay, so microscale in the mesh kind of a form, and then you have these veins which are big veins which are going into the leaf, or those main structures are kind of a mm scale, and then they span large area. Okay, that is a kind of other nature of the structure. So we want to kind of mimic these structures in some kind of a way. So how do we do that is a question. Okay, so if you think of conventional ways, you can think of what ways come to your mind if you want to think of fabricating such structures. Okay, so we are not only talking of microscale, but microscale now connected to the bigger size scale as well. Okay, we can of course do is simply at microscale these structures, no problem. But what we are right now looking at is both microscale and further we'll see how this can be further extended to nanoscales as well. Okay, so if you think about if you have some kind of a lectures gone through this course, you might be saying that okay, look, for microscale fabrication you have these lithography processes. Okay, which can be used for getting to these structures. But typically these lithography kind of ways of doing things, or micro 3D printing based kind of ways of doing things with this 2-photon absorption here are limited in the range. Okay, they cannot produce structures of very large kind of a size. And even if you can do the stepping kind of a phenomena, you can fabricate some small structure and then step it over and get larger structure and step it over again. Like that you can build, but it's quite time consuming if not infeasible. Okay, in many cases, fabrication is quite infeasible given the amount of time that is required to kind of get these structures. That is from the lower kind of a scale manufacturing, like micro scale or nano scale manufacturing side. If you look at it, the range is a issue, and the time taken for fabrication is a big issue. If you go from our normal kind of a fabrication, big size kind of a ways of our fabrication, you'll see that these systems, as compared to the nano scale or micro scale technologies, will have a very poor resolution. Okay, so this resolution that is obtained by these machines is going to be poor. Your minimum feature size you cannot machine less than say few hundreds of microns. So there is this kind of a tussle between the two parts, resolution and range. Okay, these two are quite they are not always together. Okay, if you have good range, then resolution will be a problem. If you have good resolution, then range of the structures is going to be a problem. Okay, so we want to kind of see, okay, how we can fabricate these both together in some kind of a way, and also in inexpensive kind of a way and time efficient kind of a manner. Okay, so this is where some kind of the conventional ideas may not kind of help us to think. We need to think out of the box and come up with something which is completely different from what methods that are already there in the literature, not getting biased by them. So that's where we have this inspiration coming from the nature. I need to change the pointer again. Okay. So you can see that, okay, this is inspiration taken from some art form of fabrication of this kind of geometries on the paper. So I hope you can hear the video. So how do you get that is you see these two pieces of glass here, and then you have some colors with a sticky substance here. This is some kind of a gum that is taken. Okay. Then you mix that, and then you paint it on the glass. Okay, you paint it in the sense you just put a drop of it on the glass. Okay, you don't really kind of paint it geometrically. Okay, so you get this color transferred to the glass. Okay, some amount. Okay, you can have multicolored kind of possibilities. Okay, so I'm just giving you this kind of thing to give this process, how this process really happens. Okay, so this kind of a color combination you can have for this art. Okay, then what you do is that you actually take another glass and put it on the top and press it. Okay, that's what we are doing there. Okay, it gives a really nice kind of a film here. Okay, and now we start separating. And you see these structures have started emerging already. Okay, so you can see these geometry structures are getting fabricated on the surface, and they have this nature. They are thicker in the middle, and towards edges they are very thin. Okay, and then now one can transfer them on the paper. Okay, so that's how this art is created. Okay, now we can use the same process. Okay, so we can see some of the fundamentals of fluids, what are which are working there. So if you see that, this is how the structure is getting transferred here. Okay, and you can get this nice geometry on the surface, and it is scalable. You can see that this process is scalable. You can get as big as you want to get these structures. And you can see that they have one branch connecting multiple branches together, and then the multiple splitting of the branches is happening here. Okay, So let's move on to kind of seeing like how do we engineer now this concept. Okay, so let's get back to the science here and see what is the phenomena that is happening here, which is giving you.
Excuse me.
Yeah, Kiran, anything?
Yeah, I think you are not in presentation mode. I've pinned you, so then it is able to see the screen, but not all other are able to see. So can you go in presentation mode? That will be better, I think.
I'm in a presentation mode only here on the screen. So is it not visible?
It is visible in one corner of the like total screen.
It is not in the screen mode, sir. It is in the only one corner, sir. Short screen, sir.
But for me it is full screen actually. I mean, on my screen I see the full screen mode, but so you unpin me myself.
Yeah, I will unpin.
If you unpin, then like your screen will be visible.
Yeah, I have unpinned. Now it is on one corner. If it is pinned from my end, then it is visible for me. But I think other people are telling that it is not visible.
Sir, you have to present yourself.
So
you have to click on the present now, sir, on your desktop or laptop.
On the desktop, present now. Huh? Where is that?
That is at the bottom.
Okay, see, got you. So resume presenting. Okay.
Yes, sir.
Yeah, it is.
Yeah, it is visible, sir. Yeah.
It is visible. Okay.
Yeah.
So, yeah. Please let me know if at all any other kind of problems are there. Don't
Okay.
be shy about that. Okay. Great. So we now move on to the science now. Okay. So we see what is the phenomena that is working behind this process that you saw just now. Okay. So this in the fluid dynamics domain is called Sackman-Taylor instability. Okay. How this instability is produced? See, you have a plate here. Okay. And other plate here, okay, and in between the two there is a fluid that is squeezed, and now you are pumping like some kind of a low viscous fluid, relatively low viscous fluid inside. When this fluid is pumped, it spreads inside in some form, but if you see the top view, it actually spreads like a fingers. Okay, this is called fingering instability. It's very well known in the literature called Sackman-Taylor instability. So our idea here is to fabricate structures by exploiting this, the Sackman-Taylor instability to give the shape to the fluid. So we are giving some kind of a shape to the fluid in this kind of a fractal geometry form, and then next idea is to retain the shape, okay, to get the structures out of that shape. So this is the main kind of a different kind of a thought process that we are carrying out here, to shape the fluid first and then retain the shape in some kind of a way. Okay, and for that we'll use this mechanism of this Sackman-Taylor instability. So this is a radial kind of a Helle-Shaw cell, in which this apparatus is called Helle-Shaw cell, in which this process is done. And what we are actually trying to propose to do here is not having this kind of a hole here for the low viscous fluid to go or pump it. What we will instead do is we'll separate these plates apart. Okay, so that is what we'll do here. So you take a fluid drop, as we have seen in the video, then you compress it into a form of a film. Okay, once this film is formed, you'll get some kind of a pressure distribution inside the film. The pressure will be maximum in the middle, and it will slowly come taper down towards the end in a kind of a parabolic kind of a way. And then you separate these plates out. Okay, this is the angular separation that you can see here. And when you do this process, what you are left. Okay, so then what is going to happen is this fluid compressed film is not going to go back as a again. Let me get a laser pointer. It will not go back as a drop. Okay, so since the air wants to rush fast inside, but the fluid cannot move so fast, then the air that is trying to rush inside from the edges will puncture this edge at multiple places, as you can see here. And then the air will pass through those places. And then as the air passes through, it leaves behind this kind of a fingers of the fluid, viscous fluid on the surface of the substrate. Okay, so this is the structure that is getting formed. And you can see here there is one structure here and exactly a mirror image structure on the other side. Okay, it's kind of a two structures you get formed in one kind of a go. So now, natural question is, okay, well, look, this is the instability. What is of its use? Every time I do this process, I'm going to get different kind of structures. I'm not going to get exactly similar structures every time. Okay, yeah, agree. Completely valid kind of argument to do. Okay, so they are typically random structures. Although these branches are connected, you can see one branch is connected to every point in the structure. Okay, so this one branch is split into multiple branches, and multiple branches splitting is observed here, but it is completely random in nature. You cannot kind of say, okay, next time I do, I'll get exactly the same kind of structure. That repeatability or robustness is not there. Other thing is these structures typically are, if you do this with say fluid like oil, which is viscous fluid, they'll not retain in this shape. Okay, there needs to be some way to kind of retain the shape. Okay, they'll get retracted as you'll see in the next video, and then we can see, okay, the scalability is there. So now these questions are, how do you retain these structures? How do you, this process is scalable, you can kind of appreciate that. But now the main question is, how do you obtain repeatable, controlled and desired topology, okay, rather than this kind of a random kind of a nature of the thing. So this random phenomena has been studied a lot in the literature for many different kinds of applications. So we'll not get into that details, but we now get into how we can intervene into the process and get to this controlled topology. Before that, you can see here a video about how these structures can get retracted if they are not done in the proper way. Okay, so you see here is a oil like a fluid, and now these branches are formed, emerged, but as you allow it in time, these branches get collapse together, and finally they become a single drop. Okay. So this all will get kind of collected together. These structures are not really retained in this case. Okay, so this is what will happen with the normal viscous fluids. So we need to kind of develop some kind of synthesize some kind of special fluids to have something called yield property. Okay, this yield property will have them actually stay there on the surface. Okay, although they are liquid form. If you see in the video, the previous video that we saw, where the structures are getting transferred to the paper, they are retained for a while. Okay, with a Fevicol-like substance, which is gummy substance. So viscous substances will make sure that these structures will retain on the surface. Okay, for a while, and then we need to solidify them by different means actually. So we'll see soon what way we can do that. Now you can see the scalability of the process. So this 50 mm scale, 100 mm scale. Then you can go to 200, 150 mm scale, 200 mm scale, like that. All the scales, you'll have these similar kind of structures evolving. Now, the non-dimensional process parameters need to be controlled to kind of have similar structures happening. Say here you see more thicker branches here. Here, you see relatively thinner branches, more number of branches. This is all dependent upon some of the process parameters and properties of your liquid that you are using or fluid that you are using. Okay, so we have done a lot of calculation and studies about that, and come up with these non-dimensional numbers by which one can kind of predict this kind of behavior and get these structures done in proper way. So this is a further higher dimension of to 300 mm kind of a scale, and with some other kind of a fluid, you get these structures. So you can have by controlling the properties of the fluid, you can get these different kinds of structures. Although so far we have not seen any control of these. Okay, they are all random in nature, and you cannot say, okay, I want one branch to split only in 2 branches, and then again split further 2 branches. Like that, it should happen for 5 generations. That kind of a specification we don't have right now to generate any structures of that kind. Okay, so far. Okay, so now we'll see like how do we intervene in this process now further. But before going that, to get this process done, we need the machines to carry out this process in a controlled fashion. Okay, so we work on this fabrication of these machines, and one of our PhD students, Tanvir, he actually worked with a lot of different ideas and finally came up with this angular lifting idea with the remote center of motion kind of a principle with the compliant mechanisms done here. Okay, so what we want is actually the one plate to lift from the other plate in with a remote center at this location which is on the surface of the plate. So to get that, you cannot normally get that by using our hinge joints. Okay, there will be a lot of errors, and this is now these processes are happening in the accuracy of few microns, the speed or the gap itself to begin with is about 50 microns kind of a thing. So your normal hinges and other thing may not work well there. So what is done here is used remote center of motion or remote hinge by using compliance in the linkages. How did we do that? Is that okay? Look here. You have a simple kind of a cantilever structure, and then there is a higher plate here. This end of this cantilever is just inside some kind of a small cavity. And as you start lifting, like applying force here, this plate moves as if like there is a center here. It doesn't. This point doesn't shift on the surface. Okay, and it's simulated here, and this is actual fabricated structure part here. So when you move these down with applying some force here, then this plate is naturally moved in a way that it is getting lifted off the surface with the hinge point which is not moving. See, if your hinge point itself starts sliding here, then you will have a problem. Okay, your fluid geometry is going to get shifted. So to avoid that, this kind of a angular lifting by using principle of remote center of motion is done. And then the machine is designed to do that. This all development is done in-house. Okay, so there is a flexure guidance in these flexure bearings, which is move this block completely in a straight line fashion. There is some kind of a load cell that we are using here with a linear encoder to measure the force and the displacement here. And then a small point is attached to this. You can see this compliant linkage here, and then there is a connection between this point and the plate to kind of apply the force to the plate at one of the ends. Okay, so this is how you have this mechatronics or there is the actual machine coming up for this kind of a process. And this is another kind of a way in which we are doing the parallel separation here. Okay, so you are having this bottom plate and top plate, and you can have parallel separation. So there are these two kind of ways of separation possible. Okay, and they'll have some kind of advantages, disadvantages, and things to talk about. Okay, so with this now we start doing formal experiments. Okay, now so we can carry out a lot of experiments with the controlled parameters with these kind of setups, and there is no big kind of technology as such coming here. It's simply something elements put together to get you these kind of devices. Okay, and this can be made by anybody. See, we can do it manually. Process also can be possible. So I can think machine is not a big deal to develop for such a process. So you can see here the small little video of how this operates. Okay. So you can see this is a compliant mechanism here, compliant linkages, and then there is, if you see here, there is a ball which will kind of move down to kind of compress it. Okay, so this plate is lifted now. Okay, so like that you can see here again. You can see. So this plate is getting lifted. Okay, and it gets lifted as if it is rotating about the end point, which is a remote center of motion of this compliant mechanism. Okay, sorry. So now, so the idea to kind of get now the control structures. Okay, so we want this one branch splitting exactly into two and further into two. That's what we are talking about. So the idea here is to kind of see these fingers. Can you see these small little things? They are actually small slots or some surface scratches made on the surface of the acrylic plates that are used in the process. Okay, so these scratches are where you allow the air to preferentially pass. Okay, so you are creating some kind of a pathway for the air to go into the fluid, and each of these will have a little bit of a difference in their depth. Okay, so wherever there is a larger depth, will have a smooth passage of air. The resistance to the air will be lesser in the larger depth ports or the larger depth pits rather than in the smaller depth pits. Okay, so now if you do these, okay, what happens? You can see here. Okay, so the pores, these anisotropies, they act as a preferential locations or seeds for the fingers to initiate. Okay, so all other places the fingers are suppressed because they are having these kind of a smooth pathways for the air to traverse through. Okay, and one can see that this finger has started traveling more than other fingers. These two fingers, end fingers, are traveling the fastest than the other fingers because they are the depth of the pits here are largest. Okay, so if you continue this process, then you can observe here that the other places the fingers are going in the random kind of fashion. Okay, in this direction. So you are only the control area is only in this part that is happening. Okay, and as you progress in the process now, you can see that this geometry with exactly this kind of a form is coming up on the surface. Okay, so one finger splitting into two, and again into two, and again into two. The three generations kind of a structure is getting produced. Okay, so this is a process by which one can have a nice control over the process in the form of the finger generation and finger progression as well. So this is what is going to get us some kind of a robustness to the process. Now every time we carry out this process, exactly the same thing is going to happen in this area. Although in the other areas things are going to be different. Okay, so this area you will always have these branches exactly in this kind of a form. Okay, and there might be some small kind of a shift of these nodes or things that locations may be happening a little bit here and there, but there are ways in which that can be also controlled. Okay, so we may not have time to talk about that part here, but overall the process has now a much more robustness than it was there before. Question? No, I cannot hear.
Please, Charudatta Madse, please mute your mic. Professor Charudatta Madse, please mute your mic. Sir, you will please go ahead, sir. Please go ahead, sir.
I thought somebody is asking a question. Okay, so you can see these kind of a controlled and uncontrolled parts here nicely. Okay, so this is how one can get this kind of control geometry, and this geometry has now this at a micro scale. These branches are at micro scale here, and when you come to the node, they are up to some mm kind of geometry. And if you see the thickness here, the thicknesses are going to be a few hundred microns. And we have, by changing the fluids and by using different kind of materials, you can get this branch thickness up to 6 micron down actually. Okay, so we have gotten some branches which are like 6 micron down, and width is about 30 microns is what we have gotten so far. So that is just a matter of changing the fluid and fluid properties, and one can kind of start getting these dimensions as low as you wish to do. Okay, so let's move on from here to the next slide. Yeah. So now formally we have studied the non-dimensional numbers like depth of this pit versus the the gap, initial gap that you have between the two plates. Okay, so you can see that with the larger gap, okay, this D is larger depth of pit, there's a large progression of finger that will happen when other finger has not yet initiated at all. Okay, so that is how like one can see that larger the depth, you'll have a larger progression of finger that is happening as compared to the finger where there is no depth, or like there is zero depth, or there is a small depth. Okay, and this graph looks like this. Okay, so now by using this non-dimensional form of this depth, if you have like a number of such distinct points, which are the depths which are chosen for your experiment, then that many number of generations you can get for this Cali tree structure. Okay, if you want 5 generation structures, you need 5 distinct kind of gaps that you can take up from this graph. Okay, and then like you get 5 generation structure like that. One can kind of have higher and higher generation structures possibility. Okay, so you can see that here we have formed this like 3 generation kind of a structure or 5 generation structure here. Okay, so this multiple splitting of the branches happening like many times will give you these nice little structures. Now they can be used for actual applications, and there are some parameter ways in which like this length of each of these individual branches can also be controlled to a certain extent. Okay, so that also is a possibility. So now there are other kind of forms of this anisotropy. So what we have seen so far is this kind of a pits kind of anisotropy. Okay, where you have these pits like coming in the form of a small dents on the surface of the scratches on the surface of your acrylic plate. Now we do this with a hole on the surface of the acrylic, and these holes are seeded in a different kind of a fashion. Okay, so see, some holes are closer in the radial direction to the center than some other holes, and you will have some differences coming in the progression. Now, why this happens? We have studied that in the form of numerical studies that the velocity of the progression of the finger is proportional to the pressure gradient. Okay, that is a fundamental concept there. Okay, and these pressure gradients, if you see roughly, we have seen in the first slide, it's like a parabolic in nature. So if some of the holes are closer to the radius, then the pressure gradient there is going to be larger. Okay, what it means is that the fingers initiating from those points are going to progress much faster than the fingers which are generating at places which are away from the radius. So you just need a very small data difference between these two holes. Okay, it's actually not really even conceivable very easily. So we put very small data difference, and that difference is sufficient for the finger initiation to and further progression to give. Okay, so that is the idea that is used here. So in the previous case, we used the depth of the pits as a control for the finger progression. Now here we are using whole locations, okay, or location of these ports to control the finger generation evolution. Okay, so this is how there is some kind of a characterization done in the non-dimensional number form again. So these graphs which are published in papers that I have cited here can be used directly for designing your own kind of a fluid experiment because they are given in the non-dimensional kind of a regime. Okay, so one can easily read off some things from these graphs and start using it for your own kind of a plan for development of the structures. Okay, so we are same manner we can fabricate these Cali tree structures now by using this finger generation by using the pores. Now what is going to happen is, since there is fluid little bit beyond these pores also, like they are going to form this nice little ring around the structure. Okay, so we'll see how when the structure evolves, like how this ring gets kind of formed, because this is the circular shape, like outer boundary is up to which the fluid is getting squeezed. And when the air starts getting into these holes, when we start separating, air will kind of start penetrating through these holes, and it creates this kind of a space inside, and then the evolution of the structure happens. So this is a very different kind of a philosophy of developing these kind of a micro scale or multi-scale structures, which are useful for many different biological, especially biological applications. Okay, so now you can see here how things happen. Okay, so let's first observe for this case where the structures are only on the part of the sector. Okay, you can see there is small difference between the places of these structures. These holes here. Okay, and fluid is kind of compressed beyond these holes, and you can observe the uncontrolled part will evolve in the same way as was happening for the random kind of a case. And now with these holes, now one can see this small little ring that is coming out around the structures here. And this will be useful for some cases where you want to kind of flow the fluid. You want to use this structure to fabricate flow channels. It means the fluid can flow through these branches, and then they are collected at the outer branches. Now you can see these are the kind of structures that are getting fabricated as the. So you can see these aspects of this process. This process is very, very simple, and okay, we'll wait for these things to come. So one can do this now with the maybe. So one of the aspects of these structures is this process takes hardly any time to evolve. Okay, you can just compress and the separate the plates. That much time it is going to take to get these structures fabricated. So it's like a few seconds, these structures can get evolved, and that has a lot of implication from industrial perspective or actual usage perspective. Okay, so these can be used very easily without any kind of lithography machines that you may need for these. So what you may need is just some ways to kind of drill these holes on the surface of the acrylic plates, and then the plates can be utilized for many different kind of forms fabrication by changing the fluid properties. Okay. Now we see in this video now the same thing done all through the periphery. Okay. So what you see here outside here, like a stick, they are actually the shadows of the holes. Okay. So don't worry about that. This is the shadow of the hole that is drilled in this acrylic plate. And then now you can see this completely symmetrical structure getting evolved as against the random geometry that we have seen in the previous kind of cases where you don't have this controlled geometry evolution. Okay, so this kind of gives you the similar structure that you have seen for example heat exchanger possibility. Okay, so this is a kind of the structure that you can generate by using this process, and you can see these multiple generations are located at pretty decent kind of locations here, and we'll talk about this part of the process later. Okay, so this is what is controlled by patterns which are multiple generation control. This is a first generation only control where you have all these end branches equispaced. Okay, but all other things are evolving randomly. Okay, here first generation is controlled. Okay, and then you have these two nodes where you have this all the end. You can see this first generation triangular branches coming up. Like that, you can have multiple generations controlled. Okay, and this multiple generation controlling, you can get very elegant kind of structures fabricated for different kind of applications. Okay, so still I have not talked about how do we create these structures out of these fluids which are ceramic slurry based, where you have a ceramic powder mixed with a photopolymer. Okay, so these polymer ceramic kind of mixes are there, and then once they are formed, they retain the shape because these ceramic particles have some friction between them, and that gives these fluids a yield property. And once they are there on the surface, we just need to solidify them by using some kind of a UV curing or thermal curing of the polymer, and like you get polymer ceramic particles mixed in polymer matrix kind of structures. And one can see that now if you are getting these ceramic structures or ceramic green forms like that, one can sinter the ceramic and like you get really sintered ceramic structures also, which we have done already, and they come very beautiful, very strong structures. Now with the ceramic structures, we can kind of cast metal on them and like do a lot of different kind of processes. So, and this is scalable. This can be done at larger scale. One can use this as some kind of a engraving on the surfaces or some texturing on the surfaces can be possibility. Okay, so far about these fractal geometry kind of forms of these structures, and one can have now different plans coming up. I mean, depending upon how do you kind of see the things. Right now, we have just seen the calligraphy kind of structures coming up, but one can have many different kind of possibilities if we have the depth control happening in a different way. Okay, for the same kind of a fluid, if this depth and diameter of the holes positions are controlled in a different way, you can have many different kind of a family of structures that can evolve out of this process. Okay. Now let's move on to little further more characterization of these branches. If you see these branches, they look like a Gaussian shape here. Okay. So there is a cross section. Naturally, coming up cross section is a Gaussian in nature. And there are some ways in which this cross section can be tampered. So first we see the cross section at these lower generation branches is small in size, small in depth and diameter, and in the larger generations you get like a bigger kind of a cross section and bigger depth here. Okay, although the shape is always Gaussian in nature. Okay, and then these structures are mirror images of each other, as I said. So one can kind of join these two Gaussians on the other two sides coming together, and one can kind of get full geometry stuff. When we transfer this geometry for example, for the application of fluid flow channels. Okay, so these structures are right now protruding on the surface. One can kind of cast some material like PDMS on these structures, and one can get like a dents of this shape. And those can act now when covered by a glass on the top. They'll act as a channels. So we have done all that to get some kind of a microfluidics kind of application going on with these structures. So now let's talk of a little bit more enhancement into or more control over these structures in the form of multiple pores. So as we have seen, when the fluid is compressed between the two plates, the shape of the pressure gradient or pressure profile is going to be somewhat like a parabolic nature. Now, if we do like a multiple holes on the surface, the pressure shape is going to change here. Pressure profile is going to change, and these multiple holes each of the holes will act now as a port for the air to preferentially pass through. Okay, so air will not kind of if your air finds a pathways here to get into the fluid, it will not necessarily go from the sides. Okay, so this is the idea here that okay, we create a preferential pathways for the air to pass through these holes here. Okay, and with these very interesting kind of geometries now can come up on the surface. Okay, so what happens when the pressure gradient is almost like a flat here, you get every hole is actually generating a circular geometry. See, in the previous cases, the hole, the profile or the shape of the progression was somewhat like an elliptical shape. Okay, it was not circular at all. Okay, so you can see here there are multiple kind of shapes drawn here. This is how the finger progresses. Okay, the finger progression is not is like an oval shape progression here. But when you have this pressure equalized almost by multiple kind of holes, then because of the symmetry, and if you use additional symmetry also, then you see that okay, this pressure gradient gives you kind of a circular progression of the fingers. and that's what one can use to generate now different geometry. So now we again characterize with a single code what is the geometry that will evolve, okay, and in terms of some kind of a non-dimensional numbers here, okay. This is a capillary number here, and then there is a radius of this circle versus gap. Okay, this B0 is a gap between the two plates, and R0 is an initial radius to which you expand or you squeeze the plate. Now one can see that beyond this point, this is a very important line here. Okay, this line signifies that all the conditions of the geometric and the fluid parameters here are going to kind of give you stable progression of the fingers. There is stable growth of this kind of a circular geometry that is going to happen, and below this there is this kind of a multiple fingering that is happening because of this instability. So instability is somewhat getting controlled in this domain, and here you can see the instability displayed because of the kind of set of parameters that are there. Okay, so we work in this domain of system parameters to make sure that we don't have any parasitic fingers that we don't want to come up. Maybe there are some applications where you want these fingers also to be there. You can have that, no problem. You can use some of the parameters which are in the domain where you want to have actually additional kind of fingers coming up inside, or additional kind of a fluid channels coming up inside. So here we have some more kind of results of some analytical formulations versus the numerical formulations and experimental. All these kind of studies have been done and have been published in one of the papers recently. So this gives you very interesting, nice control over the way the fluid will flow in such a kind of a Halley-Shaw cell, and which was not there in the literature so far, because and when this kind of controlled kind of a flow geometry is there, one can study the fluid behavior much more nicely inside the Halley-Shaw cell. So, for example, there are no results in the Halley-Shaw cell, where experimental results can be directly compared with the simulation results. So people have studied the simulation and qualitatively said, okay, this will happen, that will happen, but no result was there before which will compare actually the simulation and experimental results in one type of go. Which was made possible by this process because we have now controlled evolution of the fingers taking place in these kind of cases. Okay, so that was a big advantage for, in fact, from the principal study of these processes perspective. And one can see now with these multiple holes arranged in certain kind of a fashion. Here now the holes at the center of the square. For some kind of a square array, okay. So then that square array will get evolved, okay. So this is how the evolution will take place, okay. What is happening here is the holes are getting giving a way for the air to kind of progress in the circular form in the fluid fin, and when this circle from one starts interacting with the circle from other. Okay, they start clashing with each other, and then the forces that are there inside the fluid, they balance in certain way to kind of get this geometry coming up as a straight line here. Okay, so this is like if you have heard about these Voronoi kind of a diagrams, this process happens. Okay, so when these circles interact with each other, wherever they touch each other, the straight line forms there. Okay. And then these patterns evolve in a very interesting way to give you an array geometry now here. When the ports are multiple ports which are everywhere on the surface of the Halley-Shaw cell, like you have these multiple ports coming up, multiple array kind of structures coming up here. So this is like a square array that is getting evolved as you see in the simulation here. And there are kind of we say if you have an increasing capillary number, then this geometry will start getting these fingers here. Okay, so if you don't want fingers, you keep the capillary number low, and you will kind of get into this kind of a form of geometry. Okay. and similar kind of, you can see the structures here with a very low capital number. This is the kind of a geometry which is coming up here for all the the unit cells, and this is the geometry where the higher capital number of this kind is there. Okay, this is like a simulation, numerical simulation is carried out with in collaboration with one of our colleagues here, Samita Bhattacharya. His group is involved into this all these numerical simulations of different kinds, and we are collaborating with him to kind of get this numerical part of the work going on. So now you can see this process for multiple holes happening. Okay, so this is what we have seen already in the previous graph. Rush this, and then we can see here now the different geometries that are coming up. Okay, this is the first kind of without holes only on the periphery, and now we'll have some structures which are with geometry which is all over, holes which are all over the surface. So this is a triangular structure that is coming up. It's such a beautiful kind of structure that evolves out of these multiple holes arranged in the each one at the centroid of the triangle. Okay. So one can think now that okay, where this hole should be placed, or getting some other kind of geometries evolving out of this. Okay. So you can have now these different forms of regular array kind of structures coming up at different scale. So this is 8 mm scale, and at the same scale you can see this such a small kind of a structure coming up here. Like that, you have honeycomb structure coming up. We have actually replicated the leaf venation. I think this image is not showing up here, but this entire leaf pattern can be replicated by putting the holes at the locations which are centroids of the different polygons that are formed by the leaf veins. Okay, so that can be done, and you can get this leaf venation replicated as well. Then one can have this array and branch geometry together connected in some kind of a fashion. So a lot of these kind of variations, once you have this idea, okay, then based on this idea, one can kind of see that there are many different possibilities that are coming up. Okay, yeah. How are we doing in time? Okay.
We have time up to 3 o'clock, sir.
Yeah, sure. So you can see this video now of the entire process in some kind of a summary. So you start off with these are the setups here. The operation typically begins with creating some kind of a small geometry on these acrylic plates in form of these holes. So whatever this machine that you see here, which is some kind of a small homemade micro milling machine, okay, which uses motors which are for the aero modeling. Okay, these propeller motors, which are very high speed kind of motors that are used to do these high speed spindle or macro scale drilling. So you do this for calculated quantity of this ceramic photopolymer mix on the surface, and you can see this is upside down here. Okay, so there is this bottom plate, and then there is a top plate, and then there is this separator here. So as this touches the field frames forms on the surface. Okay, you can see that here. The touch is kind of getting into this field frame, and then you have this geometry. Now you see, if you do this process at a smaller this process at a large speed. That's what you observe here. When things are done at a larger speed, even though these holes were there in place, this process did not happen. Okay, because the speeds or the parameters were not at a values where the slow generation or without fingering kind of a generation of these branches would take place. So if you do this process now at a slower speeds with the proper controlled parameters, then you can see this geometry evolve. Okay, on the surface that we have already seen this video. Okay, And then you can have multiple such kind of things coming. Then this is a setup where you saw this angular separation happening. Okay, so there are the flexure stages, and then there is a voice coil based separation. Okay. This is again like a random shaping. So you can, it's just a thing to observe that okay, how these fingers will progress very slow and in a random kind of a fashion in the branch when there are no seeds that are there on the surface. Okay, and then this is angular separation because like you'll find that then there is hardly any branches here, but the branches here are progressing faster. Okay. So like there are many different kind of patterns. This is like a simple ring kind of a structure. There are like different patterns that are coming up. Yeah. So this is like a ring which is having multiple branches inside and outside both. So in summary, like you by using this process, one can develop these different kind of patterns which are there. Now the under control can be possible for this further. Now that work is going on about is by using some fluids which are polymer what do you say suspensions. Okay. Instead of ceramic kind of a particles which gives like particle based fluids will typically give this kind of a Gaussian variation of the cross section, but then if you use polymers which are mixed with some kind of a volatile solvent, then they are going to kind of give you these kind of thin branches. And these branches, if you see this Z geometry here, like they are like a few microns in height. Okay, and then say this build it is about 30 to 50 micron kind of a thing. Okay, so these are really one can, if you want like the cross sections to be controlled in the rectangular fashion versus like there's kind of a Gaussian fashion, one can use these fluids which are different. Okay, so we can change now the branch cross sections also. Then this can be inverted, the geometry can be inverted to get into this PDMS, this kind of, it's like a rubber-like material in which this geometry can be replicated to get you these troughs instead of like protrusions. You get now these channels. Now these channels, if they are covered from the top by using a glass, then one can have a fluid flow happening through that nicely. And we have used that especially for this array kind of geometry to create this kind of a device for studying the drug screening or drug effectiveness. We can study in such a device. How we do that is we have this this device, this array kind of structures. We have a reservoir here which will contain a drug. Okay. Now, when you have reservoir here and there is another like a dummy reservoir here which is having no drug or only the fluid, then a gradient of drug molecules is set up across these different branches here. And if you see the cells at the nodes, those cells are going to kind of get to see the drug at appropriate concentration depending upon the node location. Okay, so the nodes which are very close to this reservoir will have very high gradient of very high concentration of a drug, and then which are away from that will have a lower concentration of the drug. And these all things like has been done to establish this drug gradient, and then to study like the cells have been seeded, these devices are being made, and we are right now like in the process of getting the results for actually the death of the cancer cells in this kind of a device. So this can be used then for tuning the right quantity of the drug that is needed for cancer cells to die. or what is the quantity of the drug that should be given to the patient to make sure that the cancer cells for the patient will be definitely cured. Okay. So that is how we can carry out, like, the application based research. So here we have a collaborative this research is with collaboration with another professor Abhijit Mujumdar from chemical engineering department, and his group is involved into this chemotaxis kind of application. Is other kind of in which this process can be used. So without using lithography, you can create this kind of a microfluidic channel based device which can give you these the drug screening platforms for them. There are many such kind of possibilities that are there. I mean, one can say that, okay, we can fabricate really our veins kind of a geometry by using this kind of a fractal geometry structure. Okay, so you see endothelial cells around this geometry fluid channels, and then you can get actually these your blood veins and the geometry replicated on the chip. And with that, we can have some kind of a lab on the chip devices made. And we have now currently some research going on in creating such kind of a chip for the blood-brain barrier. Okay, so many drugs do not reach your brain because of this some kind of a barrier that is put there. The drug molecules are big enough which cannot cross this barrier, and because of this, one cannot administer the drugs to the something that will happen in the brain. So this is some kind of a protective mechanism of the brain but then the flip side of it is like one cannot kind of cure anything that has happened wrong in the brain. So to have the drugs reach to the brain, like you need to overcome this blood-brain barrier, and to study that on the chip, we are designing right now with again collaboration with Monash University. We have a student, a common student going on. She has already fabricated a blood-brain barrier chip, and she's carrying out now these cell seedings and the barrier strength studies right now. So these are different directions in which this kind of innovative application of some of these geometries is taking off in actual applications. This other kind of experimental work that some of one of my PhD students has done on actually two of them. Is Prashant and Prasoon, both are PhD students here in Monash Academy, and they have done this fabrication of leaf mimicking microporous micropump kind of a structure. So what is done is this small little kind of a vein geometry that you saw, which we have used. This is they have, of course, they have not used it in a form of a controlled structure. This is like an uncontrolled kind of a structure, and randomly evolved structure. But what they did is this geometry also on one side, and on the other side it has been this is a filter paper that is connected to it. So what happens is, because of this geometry, the fluid finds a easy pathway to connect to the filter paper, and that's how the efficient pump can be developed. So this fluid, when it's connected, it can pump really. So this is a graph of actually the experimental and analytical kind of a graph showing the effectiveness of the flow that will happen in this kind of geometry with without this geometry and with this geometry. There is control geometry is there, and there is a geometry which is leaf mimicking micropump. There is at least two to three-fold enhancement in the flow rates that is demonstrated. Okay. And then this is against the head also. Okay, so if you have different head of water which is pumped, then you'll have a different flows that are happening. But in general, you'll see that this kind of geometry will give you much better kind of enhancement in the flow. So there are many different kind of other applications that this is getting used now. So this is one of the silver electrodes with the spectral geometry. So these are the silver lines which are in the electrode kind of a form, which are used for the electrode kind of application in the fractal geometry form. Okay, and then you have these microchannels which are connecting the paper fluidics. The paper is a thing to kind of get a capillary pump system going. Then you have this sintered structure with the ceramic. Okay, so these are really hard structures now on the surface of ceramic, and one can kind of cast material on them. This I've talked about already. And then we are doing some studies with the blood flow with the fingering instability. So that's a very interesting kind of a way the red blood cells in the blood gets kind of accumulated at different places based on the way the fluid flow takes place. And this is a leaf venation that is indicated here. Okay. So in conclusion, we have this kind of a novel process that is proposed here for doing this micro nanoscale kind of especially microchannel kind of geometry or fractal geometry, which can be used for many different applications. And the interesting thing to note that overall area of the structure can be a much larger scale as well. We are right now working on a system which is, or we have already fabricated a system, I'm not shown the results here, which can fabricate these structures over as large as about 300 mm or 350 mm diameter. Okay, that large structures can be fabricated with these kind of features which are at multiple scales, and they can be useful for in many industrial applications, especially heat transport, mass transport domain kind of applications. We may find some change if at all. If these structures, we can easily transport it to some kind of a metal geometry, metal material. Okay, so that's where some of the efforts are going on in that area. And there's other kind of research going on is extension in the third dimension. That we can really produce structures which are having like a thin tube-like structures or thin ball structures that can be. So it's like the same geometry. You can imagine if it is extruded in the third dimension, how it would look like. That kind of a thing it can be possible. We are right now working on that based on some kind of fluids which are having some different nature to them. Okay. And there are several collaborative research possibilities that can be there. I mean, if any one of you are interested, we'll be happy to provide you some of these structures to kind of see some applications that you want to develop. If you say you come up with your material or something, we can kind of give you access to the machine to create your own geometries and work with for whatever applications you would like to do. There are a lot of these unexplored domains. The sensor is one of the domains. There is a lot of possibility I can see. In energy, there are already some kind of work is going on. We have found that these fractal geometry electrodes are especially quite useful for supercapacitor kind of application. Okay, so some students are developing that supercapacitor kind of application. So although looks like somewhat kind of an easy process, or it has a lot of different implications in different domains of application. When I talk about this to some places, people will start thinking in their own kind of domain if they can be applied. So say this chemical domain, for example, the catalyst can be having this kind of a form, so that its efficient surface area of the catalyst can be utilized very efficiently for any chemical reaction to take place. So there is since this is inspired from the nature, and nature has some kind of optimization on done. I mean, these structures are attracting a lot of these different applications, I would say. Okay. So I would like to thank you first to kind of listen to this talk and appreciate your especially after the lunch. Okay, immediately it's very difficult to kind of keep up with the presentations like this. But hopefully, like, you are awake still, and like, I hope you have kind of gotten some ideas and things to kind of for your future to work on. And I must acknowledge like some of the funding which is imprint grant with the DST and MHRD both for this research. So DST was 50%, MHRD 50%. So it's one of the big grants that we have got for this project to really progress on many different aspects of these activities. And we have Samita Bhattacharya and Professor Abhijit Mujumdar, who are collaborators for this imprint project to work on the simulation part of it, and then some of the bioapplications part of it. And Raj Moshwala I have to thank for initial grant to set up this Suman Moshwala lab for when Kiran also was there here. He enjoyed working in this lab for his particular work on bulk lithography, which I hope you may have a chance to look at it in these coming few days. And then, of course, this work does not progress without PhD students and tech students and others. Okay, so this is a big team of students who are really behind all what you have presented, and would sincerely acknowledge their contribution and relentless efforts putting hours in the lab to carry out some of the very interesting results, and getting them corrected multiple times to make sure we do the things towards perfection. Okay, so all of them are very enthused students, and some of them still working in our lab. Okay, so we have industry partners here, Dhananjay Dendukuri from Ashira Lab, and we have Arun from Strategy Automation. With Arun, we built a very interesting micro milling machine, okay, to this imprint project, which can do this job over the large kind of a size of the plates. Okay, so to get these holes, different holes drilled at different locations. And with Ashira Lab, we are developing some of these blood plasma separation and those kind of initial, some devices for the biodomain, which are coming up with these insights into practical application needs. Actually, okay. So that's what I thank you for this. And if there is some time, maybe I can take some few questions.
Thank you, sir. We'll take some questions.
Yeah.
There is a raised hand by Professor Velmurugan.
Yeah.
Yeah, Professor, please have your question. Professor Velmurugan, sir.
Yeah.
Yeah, please, sir.
Yeah.
Please go ahead with your question. I think some problem is there, sir, with the internet.
Okay.
Any other questions? Any other question from the participants?
Good afternoon, sir. I'm audible.
Yeah, you are audible. Please go ahead.
Yeah, sure. Good afternoon, sir. Myself, Rajat. I'm just working an assistant professor in a college, and I'm just working as well as I have a startup company. And my question is that I am working with this MEMS, actually paper-based MEMS particle. Actually, we are working with the piezoresistive sensors, and this all we are working with our lab. And actually, we are still on the manufacturing process. Still, it is on the research base. And I just have when it was first of all, I have to say, sir, thank you so much. It was really wonderful presentation, and it is like we have a great knowledge and enlightening us to the new field of microfluidic, how we have to do that. So I have just question from my experience. When when we are working with the lab, we are making this minute fibers actually. So how we can check on this conductivity from your experience? Because this when you're making this for the conductivity, this fibers, it's getting the breaking when the property is losing when you press which is heavy pressure, or when you're doing the viscosity, when you changes that, or whether you have changed any property of this, then it is suddenly it's breaking, and you cannot use for like we are using same like a nano material or a carbon nanotubes. That efficiency we are not getting. So how we can avoid this situation? So I just want to thank you, sir.
So as I understand, there are two questions. How do we measure for the properties without them breaking, right? So for that, one can use something called micro manipulators. So have you used micro manipulators before, or like so when there are probes which are like two needles which are coming and like then they are touching. So we need this kind of a XYZ motion to these needles done, and they are available so you can use them as the probes to kind of probe these and like touch the fiber at specific point without applying too much pressure. That is possible actually. Okay, and then they will not break, and we can measure the properties. Now, I don't see regarding how to prevent breaking or this. I'm not probably the right person. We need to see what kind of a material you are using for creating these fibers, and that is thought and discussed probably separately. Okay.
Okay, sir. So, in your research, have you experienced any problem with this breaking of the structure, or when you're making that when you're making the structure, you had any problem with that conductivity, or how that issues how you solve, sir?
So see, we are working with fluids, okay, and we have used fluids with the particles. Now, in some cases, like where we have some carbon particles which are seated in the fluids, we created some structures which are resistive, piezoresistive in nature, and they are fractal geometry structures that are coming up. And see, for them, so there, in that case, like we used some PDMS kind of a material to create these structures, or some our own acrylate materials to create these structures. And with larger stress, they will certainly break. They are breaking, like they are getting cracks also. To overcome that, you need some kind of a fluid binders to be placed in the fluids. Okay, if you have a binders, proper concentration of binders in the fluids, then they will not break. So it's really depend upon how much is that you want to stretch those fibers and still not break. Depending upon that, different kinds of materials need to be changed to get to the geometry that you want, which will not break. So your fibers will break if they are suspended in some kind of a matrix, and that matrix is giving away. Okay, so that's where like we can change the matrix and then make sure that fiber will not break.
Okay, sir. Yeah, sir. Thank you, sir. Thank you so much, sir. Thank you.
Any other questions or any discussion needed?
Yeah.
Professor Bel Murugan, are you there?
Sir, hello, sir.
Yeah, we have Professor Vishnu. Please
Yes,
go
sir.
ahead.
Sir, actually, what is the difference between this nanotechnology and the nano fabrication, sir?
See, nanofabrication is part of nanotechnology. You cannot study nanotechnology without some kind of a nanofabrication. So see, some nanomaterials, you have to process them or do some kind of a fabrication to get to some utility for those materials, right? So there are many different kinds of ways of nanofabrication. Okay, so one has to use one of these several ways to really do some kind of technological application over there.
Okay, thank you, sir.
Yeah.
Any other discussion? Any other point to be discussed by participants?
Excuse me, Professor.
Yeah. Please go ahead. Suresh Kumar, please.
Yes, sir. What are all the fluids can be used in this type of micro machinings?
In these processes that I have talked about, you can use.
Yes, sir.
Yeah, you can use lot of fluids. So wherever the viscosity is high, those fluids can qualify here. Okay, so some fluids like a Fevicol or honey, so those kind of fluids. And if you talk equivalent of them for the engineering applications, these are all kind of a suspensions of micro to nanoparticles into some kind of a polymer matrix. Those suspensions in proper way they are prepared, they can be used for this process. You can have fibers also in those in these fluids. Actually, you can put
Okay, sir.
nanofibers or graphene you can put in these fluids. Data structures. So we are right now doing some kind of a graphene fabrication by using these fluids, actually fluids based fabrication.
So shall we use the mixture of semiconductor fluids?
Yes, I mean I've not tried, but like if you get this consistency, which is viscous consistency, then absolutely possible, no problem. Okay, so we can use like whatever particles or whatever fluids you want to use, but they should have some certain kind of a viscosity level. And we have this non-dimensional graphs. So even if the viscosity is lesser, we can tune the velocity of operation in such a way that you get whatever you desire. So they just need to obey, have some kind of a range of viscosities which can be falling in the range of capillary numbers that are there for this process. They're presented in
Okay.
these papers.
Okay, sir. Thank you.
Any more questions? So thank you, participants. Thank you very much, sir. I take this opportunity to thanks Professor Prasanna Gandhi. Sir is my guide actually, PhD and PhD student of sir, and it is always wonderful to listen from sir on these different topics. So